with Stuart today and his talk, Stupid, Awesome AI. Give it up for Stuart, everybody. Let's see. Let's look at this. How's that? They're both the same.
Okay. Hello, everyone. As introduced, I am Stuart Page. And I've been a software engineer now for about 3 years. Like a lot of people, I was furloughed during the pandemic and decided to switch careers. I figured I've always been interested in computers, and I'm a nerd, and I'm on-call tech support for my mother-in-law. So, let's go for it. And I'd been assured by all and sundry that there was a tremendous need for programmers. And so after a boot camp and an apprenticeship, I settled down into my new job as a software engineer, cushy and safe. There will always be a need for programmers. Nothing could ever take my job. I'm completely insulated from change. I'm joking, of course. I realized eventually that our robot overlords weren't coming for me. AI isn't about to replace our entire profession, the same profession I just transitioned into, yet. But now I had to work with it and build with it and develop with it. And I'm so sorry for doing an AI-based talk, but there you go. Everyone wants to talk about it. AI didn't come out of nowhere, but that didn't stop it feeling like that happened a couple of years ago. And at Revelry, where I work, we build software, and we had to figure out pretty quickly if we were going to build something interesting with these newfangled, or maybe newfangled to some, large language models. And we had to figure out, how do you keep your feet and actually build something worthwhile with them? Leaders everywhere were asking where, why, and how much of my cryptocurrency can I sell so I can invest in AI? But development teams were still trying to figure out what and how they could build on top of it, and we were no exception. And so, that said, welcome to my talk about what and how to build on top of it. The first half of my presentation will focus on how we at Revelry got into the AI game and our first experiments with AI, Storybot and RevBot. Then we're going to go over retrieval augmented generation and get into how it works. We're going to talk about our decision to build in Elixir and get into some niceties like how we modularized our code and implemented streaming in LiveView. And so don't panic as I'm discussing AI stuff or anything we build using different tooling. I promise discussions of Elixir and LiveView are coming in the second half. So let's go over some definitions. You know what AI is. I don't have to tell you. It's an unstoppable killing machine. It's a reflection of our own humanity. And it's a replacement for children. That's a deep cut. It is the name of any technique built to mimic human behavior. And in this talk, you can just assume that I'm talking about LLMs and not reinforcement learning or classic machine learning or anything like that. Which brings me to large language models, a type of AI that predicts textual outputs. Just think, ChatGPT or Gemini or Anthropic or Llama or whatever floats your boat. All you need to know is text in, text out, like autocomplete on steroids. Then there's RAG, which is retrieval augmented generation. This is a technique used to add more data to a given prompt. Don't worry about that. We'll be going into that in depth in a second. And then LangChain, which is a framework which is incredibly powerful and very useful for developing applications powered by large language models. It's mostly available in Python and JavaScript, but versions of varying levels of completion are available for other languages, including Elixir. And so at Revelry, we were no different from anyone else in the beginning. We began dabbling with ChatGPT, mostly just for kicks. However, beyond Shakespearean raps and bizarre poems, we started to figure out pretty fast that with some clever prompting, ChatGPT could whip up some solid product roadmaps and user stories and even spin out semi-working code examples based on those stories. And so we decided to mess with it. So we built something called Storybot. And at first, this was just a straightforward CLI tool that we ended up releasing as an open source NPM package. It's essentially just a single JavaScript file using LangChain to tap into GPT-3 via OpenAI's API before GPT-4. We threw in some tailored prompts and we injected user input, and voila, it started spitting out decent user stories right in the command line. We went a bit further with it after that, letting the user refine their story through chat, still all in the command line. The cherry on top was the ability to export an issue, export the story as an issue in a GitHub repo, which we also use for issue tracking and project management, as well as code storage at Revelry. And our key takeaway was this. There's something here and something great. We have a tool that could save developers time and money. So I have a little video of our first experiment. So this is maybe a couple of months after ChatGPT took the world by storm, and suddenly everyone realized this thing existed and people started throwing money at it. And you can see we had our an input up there that got sent to a prompt. The prompt goes to the LLM. Response streams out into the command line. Streaming is incredibly important when you're interacting with LLMs for the user experience, which I will go into later. But it was nice. It came back with something. You can say, no, that's not good. Add some more error handling. OK. I'll write your user story for you. Would you like to make any changes? No. You get the gist. And then finally, you can name it and export it to GitHub, which is fantastic. I mean, it saves me a bunch of time because it means I don't have to write user stories anymore, which is fantastic. So all that's great, but I hear LLMs are better with RAG. And I'm going to take a little detour right now and explain exactly how data injection into a pre-trained LLM works. Considering who you all are and everything I've heard today, I am sure you have heard the term retrieval augmented generation, or RAG, but if you haven't, don't worry, I'm going to break it down for you. So any given large language model has been trained on a data set, an overwhelming amount of information that it has on hand to answer your prompt. The only tool you have to guide that LLM is your prompt. When you ask the model what you want, like say, for example, if you questions about Elixir. You can ask, how do I inspect a variable? Or like, who wrote the language? And using that vast data set, the model will attempt to answer your question. But if you ask it a question and the model wasn't trained on that data, it won't know the answer and it will refuse. Or worse, it will hallucinate, i.e. make up an answer. So the only way into the model is the prompt, and the model doesn't have the data you need. Maybe we can just inject the data into the prompt. Absolutely you can, and that's really the essence of retrieval augmented generation. It focuses the LLM on the data you provide and therefore gives better results, right? As well as guarding against hallucinations. But there is a problem. Prompts can only be so long. Or to put it another way, there's only a small window where you can provide the data. The size of this window is called the context window. You can only provide so much information before the LLM won't be able to process your input and refuse you. So if you want to paste in your entire code base to your prompt, you are out of luck. And there's two ways around this. Either you can increase the size of the context window, which everyone's been working on relentlessly, or you can only provide information which is relevant to the question you're asking. And it's this second point that you, as a developer working with an LLM, can do something about. So how about if we used a vector database, which is a type of database where all the data is encoded within matrices, and we use that to store a representation of our GitHub repo or whatever source of knowledge we want. And because of the dark magic of vectors and matrices and lots of things that you have to read a lot to understand, and even then it doesn't really quite make sense, similar meanings are stored more closely to one another inside this type of database, which means that you can use semantic search or search via the meaning of things to find the data you want. And suddenly, boom, you can inject relevant data into your prompts. And if none of that made sense, here's an example of what it looks like in practice. So before we go to the LLM, we choose the piece of the query we're going to vectorize. We vectorize the whole prompt, part of the prompt, whatever takes you fancy, whatever you think will give you most insight into the answer. Once you've done that, you translate that into a series of vectors, 1,536 of them, or whatever vectors, whatever number of dimensions your vector database was set up to handle. You then send these vectors over to your vector database, and you try and find the closest match. And the best way to do this is to picture in your head an X, Y, and Z axis. Now picture 2 points. Measure the distance between them, and the magic of vectors means that this distance represents how close the meanings of these things are. Like if you were looking for information on doctors, and the point hospital will be quite close, so that's what it'll give you. But this is completely wrong. This isn't how it works. Just look at that and think about the number 1,536 really hard rather than 3, because that's how many dimensions we're actually working in. And you got it. But the human mind is weak. Once we have our match, we can turn that back into text, inject it back into the prompt, send it off to the LLM, and get our response. Fantastic. So with all that in mind, we went for our second experiment, RevBot, just to see if we could do it. We, again, used LangChain to make a simple little JavaScript app. We uploaded our entire playbook to GitHub, and our playbook is like a huge repository of company-wide knowledge and business policy and dev environments and open source projects, whatever. And once we had that going, we added a simple form with an input box to send a prompt to the LLM, and hey presto, we were able to get back lucid responses to our questions using the playbook. And it was at this point that we took a step back. It was obvious that we had something pretty valuable here. Using LLMs and RAG and our playbook to answer our questions was one thing, but we're in the business of software development, and really we need to find something that can make us some money. And we've been writing software at Revelry for years and written thousands, if not hundreds of thousands, of pretty good user stories. And oftentimes those stories are written in a particular idiomatic style, unique to that project. What if we could tap into those stories and when we are writing stories for a particular repo and use them as data in that retrieval augmented generation flow? And of course, it doesn't stop there. You know, what if we could inject application code? What if we could focus the story using the code base so it was aware of what had already been implemented? What if we could inject proprietary documentation? What if we could reuse the prompts? And so after all that, it was time to stop experimenting and build for real. So we didn't build it in JavaScript, and we didn't build it in Python, as you can probably tell. When we first started building it out and got into the nitty-gritty, though, those were sort of the choices that we had because those were the most complete versions of LangChain. And LangChain gives you such a quick development time because it can do the embedding, it can do the search, it can do a lot of things right out of the box. But it doesn't give you much of an understanding for how that works. Or we could stick to what we want, which is Elixir. And we also get concurrency and fault tolerance and all of the good stuff that we're used to and we want. And we won't ready to give up on Phoenix Live View, right? And all the good things that it brings. So why did we pick Elixir? And I think first and foremost, to be honest, we really like it. We work fast and crucially and write better code when we're working in Elixir. And secondly is the tooling. Any app that's dealing with large quantities of data is going to need an ETL pipeline, which is extract, transform, and load, and methods of keeping things in sync. And I'm a big Oban fan, and Oban, you know what? Doesn't matter. Oban is really, really good at this. And we've worked with it before, both Oban and Oban Web. And then on top of that, you got LiveView, which is something we've been using at Revelry since it was just a commit hash in our mix.exs file. And on top of that, if we're going to be streaming responses to users, I want processes and async jobs and supervisors and just the beam, right? And finally, there's the community. The company has been a part of the Elixir community for a while, and it's full of kind, passionate people. They say flattery will get you nowhere, but you're all kind, passionate people. And we'd love the opportunity to help develop the ecosystem, right? And the cons? Well, we couldn't use LangChain. That was about it. LangChain is really nice to use, and I encourage all of you to go out there and explore it, but we'd be probably giving too much control away, which we weren't comfortable with, and we'd be locked into certain vendors. LangChain, clue is in the name, it is the glue that holds AI API-based systems together, but it gives you, it hands off so much control, and it makes things a bit obtuse. And of course, what if we wanted to use a vendor that they didn't support? So we decided to write an Elixir. Yes, we decided to write an Elixir because we didn't want to write in JavaScript or Python. We want to write JavaScript like this guy. If you've seen Programmers Are Also Human, he has a wonderful way of saying JavaScript. It's fantastic. And we wouldn't have to write Python like this guy. So we don't want to be either of these guys. We want to write Elixir like this guy. And so with that, we were locked in. We began spinning up our new Phoenix Live View application. And just a quick note to say, I love Live View. I really do, but there are dangers that lurk on the edge, and one of them is updating your app to the latest version of Live View the day it comes out, and then having to revert it, and then updating it again, and then reverting it again, and in the end, I just had to settle on a version, or we just had to settle on a version, and just like hack in the things that were a bit dodgy. But someone today told me that Live View 2 days ago, they're coming out with their 1.0 release client, so I'm very excited for that. But yes, your mileage may vary, but I love Live View, even though I hate it. No, I don't. I do love it, I promise. The first piece of the puzzle to tackle was going to be text splitting if we want to introduce an app that uses retrieval augmented generation. So in a RAG context, semantic splitting is king. In essence, making sure that you split a given piece of, when you split a given piece of text for later retrieval, you maintain its context or meaning. String.split wasn't going to cut it. LangChain does this very well. It recursively splits the given text into chunks of a given size using different separators depending on what you feed it, right? So first it's going to try and split on function definitions, and if it can't do that, it will split along flow control statements, and then it will split by new lines and spaces, which is fantastic. It maintains the semantic similarity that you need. In addition, you can overlap the chunks. And almost immediately, we encountered a gap in the Elixir ecosystem. It has some amazing AI tooling and some natural language tooling, but not for this specific use case. And there is a LangChain Elixir project, but it didn't yet implement this splitting functionality. So I did the first thing that any bad developer would try in the 2023 AI is going to take our jobs era. I asked ChatGPT to translate the LangChain splitting into Elixir code, and spent 4 hours arguing with the LLM because it kept getting it wrong, and it didn't go very well. And in the end, I just drank my coffee and thought about it and did it myself. So here's a test that demonstrates what we want. Let's say we wanted to split this text up into smaller chunks. Let's go with a maximal size of each chunk of 50 code points and a maximal overlap of 10 code points. And what we want to come out is something like this. And I can show you that in practice if maybe. Yes. I think this is good. Please still be good. Okay, good. So there is our example sentence. And we want to split it along these lines. And here's our lovely text chunker dependency that we've written. And let's evaluate that and not fat finger it. Boom. So there you go. It comes out into these nice little chunk structs. And we have some overlap. We have our start bytes and end bytes. And this is something that we can later use when we're using semantic search and get these relevant chunks, and not just in a vacuum as well, because they have that overlap. They have a little bit of context, right? That's key. And does it work on longer texts? I can hear you asking. Oh, wow, nice. Yes, it does. This is it working on Hamlet. So you can see the first chunk is the list of characters, and then we have other chunks that chunk up Act 1, and then it's going to split along the scenes. It keeps everything semantically where it's supposed to be, which is great. So now let's go back to the slides. There we go. And so incidentally, if you've been captivated by the idea of text splitting and you want to race out there and implement RAG, you can go do that. We've open sourced that. We're continuing to develop it. We welcome any contributions and anyone to poke at my terrible code. So go nuts and look for text chunker on HexPM, which is my first open source contribution. So yes. We'd already spent quite a bit of time doing what you could have done in LangChain for free. However, the time spent doing it was immensely valuable. LangChain doesn't really give you much insight into what's going on under the hood. It handles all the nasty chunking and embedding for you, and it also locks you into specific providers, which leads me nicely into behaviors. Again, a quick detour. Right off the bat, we decided to use behaviors, which is spelt correctly, God save the king, and implementations of those behaviors to modularize our code and keep it flexible and extensible, rather than dive down through the object-oriented jungle. And if you go look at the LangChain code, it really is an object-oriented jungle of inheritance. We can write a clean and straightforward behavior pattern to keep things simple. And in a reverse of an age-old trope, rather than using a time machine to hunt myself down in the past because of the terrible choices I made, in this instance, I'd buy myself some flowers and a card, because we made the decision right off the bat, when we only had one language model and one vector database that we supported, to write in a behavior to define the interface. And because of how we wrote that, it made it so easy to integrate more. And I'm sure most of you have run across using behaviors before, but if anyone hasn't, a brief overview. Let's say we wanted to implement 2 different language models. For all intents and purposes, we want them to do basically the same thing. When we throw some text at them, we want text as a response. So I suppose you could say that we want both to implement a generate function or a stream function. And what a behavior allows you to do is explicitly define explicitly define what we expect of such a generation function. What arguments will it receive? What will it give us back? And once you've written it in stone, you can then use different language models that implement that behavior, which is fantastic. It's checked at compile time, and it allows you to easily mock out the API call. It's great. I am one of the people who put their hands up when the question, do you use Dialyzer, was asked. I love Dialyzer. Here's a nice practical example of how this flexibility helped us. After about 6 months of using Pinecone as our vector database, we decided to switch up to Quadrant. This came about for a variety of reasons. We wanted to use open source, and we had a relationship with them, and Pinecone had started to get flaky, so we were faced with the challenge of swapping these 2 providers out for one another. And the interface and behavior pattern that we'd implemented made this easy. We just wrote a simple wrapper on top of Quadrant to match the inputs and outputs, and boom, as simple as that, we had Quadrant. So now we had to throw a query into the vector database, and we had some relevant data, and we'd used RAG to grab that. The last thing to do was throw it into the LLM of our choice. This brings me to generation and streaming. LLMs take time to crunch things, and time is at a premium. However, you can get bits and pieces of what you want. You can stream the response onto the screen as it is generated. Streaming is the perfect little devious trick that we can play to keep our users interested. Sure, I mean, we can all wait 10 seconds. How was that? It's worse for me, guarantee it. Longest 10 seconds of your life, longest 10 seconds of my life. Waiting sucks. But how about if we could stream instead? And then we could all simply save the anticipation. And I bet that didn't feel like 10 seconds at all. Actually, to me, it felt like 20, so. Streaming the words onto the screen for the user somehow tricks their brains into thinking things are instant, rather than taking any time at all. And OpenAI and several other language models implement a streaming endpoint, so in practical terms, you can access the chunks, they exist, you need to use them. Stream rather than generate, it's important. So live view makes it fairly straightforward to display an incoming stream for our users. It is, after all, very good at updating a page based on small diffs. I want to take you through how we approached this problem and got chunks of data from the LLM on screen. First, I'm going to explain it in words using this diagram, and then I'm going to show you an approximation in code in Livebook. So let me switch to this. There we go. So on the leftmost line of this diagram represents our live view process. The user will enter something, say, for example, asking the LLM if it likes trains or not. I don't actually do that because it gives you the most boring response imaginable. It just says it doesn't care, and it's like, come on, man, trains are great. Once you've pushed the button, the live view process goes off and calls that middle line, and that middle line is the async task. The live view process calls it with the name of the LLM we want, which in this example is GPT-4, as well as the prompt to send to the LLM. But crucially, it also passes in a callback function, and that function is what will be called to update the relevant bits of live view. So going back to the middle line, we've got the model name, our prompt, and our callback. And Elixir makes asynchronous operations very clean, and there's a supervisor somewhere managing this whole async task. But I digress. Once it's started, the first thing it does is goes over to the actual LLM, starts the streaming process, which is OpenAI in this instance. And then we come back to the middle line with our stream in hand, and then depending on what gets emitted, we call the callback function that we have. So there we go. So it calls it once, it emits I, and then like, and then finally trains and says it's ending. The callback function knows that it's ending, passes along the last message. And so on the front end, the user just sees I like trains streamed nicely. And if you're still confused about that, let's look at that in Livebook. So streaming, we can, I'm gonna have to type. What would anyone like to stream? Any questions? No? Okay, I'll just ask it if it likes trains again. Oh, thank you. Fantastic. And there's our button. We're using Kino to bring up the relevant things in Livebook. I have a nice fake live view process. It's just a frame here where our just represents the live view where the answer is going to appear. And we use that in our callback. This is that callback I talked about beforehand. So if we evaluate that, that callback is going to be passed in to the place where we're calling the language model. And so if we hit stream, rather than, thank goodness, see, lamest answer imaginable. But rather than waiting for this entire thing to generate, it streamed it nicely across the screen. I know it wasn't the best example because it was all on one line, but you get the picture. Thank you. Okay. So, conclusions. The Cambrian explosion of LLMs and applications consuming them shows that this technology isn't going to disappear. Building this application using Elixir and not just opting for an off-the-shelf LangChain solution was worth it for a couple of reasons. And first and foremost, I think it proves that if you want to develop with Elixir, you don't need to use Python or JavaScript if you want to develop with LLMs. You don't need to use any special libraries. At the end of the day, someone else is going to be doing the heavy lifting, and it falls on you to just use their APIs. And sure, you should experiment with other stuff and the easiest stuff that's available, and I don't want to bash LangChain. What they've built is incredibly easy to develop with and get started with. But if you think you could benefit from developing with Elixir instead, then you should do it. I don't think Elixir should be left out. And what we've built is proof. And lastly, it has been a blast being able to give back to the Elixir community and release something we built as open source. I might be a little biased. See, comes back to me flattering you. But the Elixir community seems to be made up of smart and understanding people. And after using so many open source packages for so long, it's been fantastic to give something back. And so that's it. If this talk has intrigued you and you want to see the awesome app that I've developed with my superb team at Revelry, come and talk to me afterwards or go and talk to Nick over there. Imagine if we'd implemented everything I've talked about, but with external software integrations and prompt libraries and multiple LLM choices and the whole 9 yards. Imagine no longer, come and see me, I'll show you. And if you're brave enough to jump right in, just go to app.prodops.ai and use the code GigCity and just go for it. We're in open beta. It's free. Any feedback is appreciated. Yeah. Building an AI application on the bleeding edge with Elixir and LiveView is stupid and awesome. But if you do it right, you too can learn to love the machine. Thank you.